Going on now to the lesson in section 1 of chapter 3, the Cartesian coordinate system, scatter plots, and linear equations. The objectives of the lesson, and then on to the lesson. Now, what is the Cartesian coordinate system? Well, for many of us, it's graphing. And we could read through this, but we'll be going over it in some detail. What we want to develop, and we'd like you to sketch this in your notes as background material. We have two number lines that intersect at right angles. The horizontal number line we refer to as the x-axis. The vertical number line as the y-axis. And then on the actual graph, once we form it, we are going to put on what are called ordered pairs. Now, these will be two sets of numbers, an x value and a y value. And the protocol for plotting on this graph, you start at the origin, and we want you to label all of this, labeling an ordered pair, the origin, the axes, and then when we plot an ordered pair, for instance, 2, 5, and we want you to include this as well, you would take the x-coordinate, and since it's positive, you would go over 2 to the right. That's the positive direction. And then move up, I guess I went over too many, move up 5, and then you put your point and label it. So this will be one of our activities. Now, continuing background information, when you plot your two axes, it divides the plane into 4 regions that are called quadrants. So this is the first quadrant, and we use Roman numeral numbers to identify the quadrants. Then going counterclockwise, the second quadrant, this will be the third quadrant, and then this one's the fourth quadrant. Now they're also indicating that in the first quadrant, both the coordinates are positive. In the second quadrant, the x-coordinate is negative, the y-coordinate is positive. In the third quadrant, both are negative. In the fourth quadrant, the x is positive, but the y is negative. Okay, this is background, and that's what they were describing in the words above. Now, we sometimes refer to this statement, a 1-to-1 correspondence. This refers to the ordered pair. The x, again, applies to the number line, the horizontal axis, and then the y, the vertical number line, the y-axis. Now, often, not too often, but sometimes, you will have an ordered pair listed as, let's say, an A, B. But again, because they are ordered, and it's a 1-to-1 correspondence, the x is always related to the x-axis and then the y to the y-axis. It seems common sense, but again, we'll stress that. You can't reverse them. They would be different unless both were the same. 3 and a 2 is not the same as 2 and a 3. That's what this is referring to. Now, in your notes, you're going to list example 1, and then you're going to write these ordered pairs down. Pause, take a moment to do so. Now you're going to take a few moments to actually plot. Again, you're just going to sketch and then put some grid lines. And you're going to sketch in, let's say A, which is a negative 3, 1. So you start at the origin. Since x is negative, you're going to move to the left 3 units, up 1, and put a dot there, and then label it A, and then the ordered pair. Then doing B, negative 1, negative 3, go over to the left from the origin, 1, then down 3, and so on. So take a moment, see what is being asked, and put that on this graph. We'll pause. Now, for example 2, they're giving us a graph, and you don't need to draw the graph, but they're asking us to identify some of the points on the graph. So what do you look for when you get an example like this? And I believe the answer would be places where the line crosses the grid. So there's one point, there's a point, there's a point, there's a point, and there's a point. So let's say these are the 5 points. Maybe on a little sketch, label these ordered pairs. And I'll pause and do it, and you can pause and do it. So something like this. Now, we are asked, how many points are there in a line such as this? And the answer is there's actually an infinite number of points. We've chosen to select ones that are on the grid line so they were easy to identify with an ordered pair. Now, for a scattered plot, for example 3, I'm not going to ask you to write all this data down, but see if you can follow it. Here is budget in millions of dollars, opening weekend sales in millions, and we're asked to take this data, and just to show you what it's like, develop, and then this is in essence the first quadrant of a graph where we have, let's say, budget along the x-axis, and then weekend sales along the y-axis. And we're taking these items of data, you can see them a little bit here, and then plotting them. So if you get an example like this, this is what it would look like. This is called a scattered graph diagram. And that would be all I would ask you to include for example 3. We saw it, but we didn't physically do it. You may be doing some in practice and certify. In our next slide, they're interjecting things that we've gone over in previous lessons and would like you to write these words: standard form, and then use this as an example, and then slope-intercept form, and use this as an example. And once you write this down, ax plus by equals c, and y equals mx plus b. Now I'm asking you to write these because this is something we're going to use quite extensively in this chapter. And as I say, repetition is good for memory. So this meets the criteria of the standard form, and this is the criteria for the slope-intercept form. Now, we're asked here to find ordered pairs that satisfy these linear equations. And there is a protocol for doing it. Now, we'll show that shortly. I want to have this as background information. Now, when it is in slope-intercept form, this one, we say the x value, and you have to write this down as well, is your independent variable, and the y is your dependent variable. That is, you put a value in for x. This then makes this side a number, and that value then, with the input of this independent variable here, gives you a value for y, which is then your dependent. Depending on what you put in for x, you get your y. All right, some background information. Now, on this next slide, what we'd like you to do is write the equation, and as we see it, it's in slope-intercept form. And in your notes, I want you to make what is called a T-chart that starts off looking like a T. Then you put some more lines into it. Put the x value there, the y value there, and we're going to actually draw a graph of this, and I actually have a line tool. Let me use my line tool here. That makes it so much neater. And you can sketch it as best you can. And I'm showing you how to do one here. What we do is we put our axes in and then try to space some points equidistant. And we want to plot points that are near the origin. So I've chosen a -1, a 0, and a 1. So now we're going to substitute these values for the x and then see what comes out as a y. Well, if x is a -1, -3 times -1 is a +3, so this becomes a 6. Now, if x is 0, -3 times 0 is 0, this becomes a 3. And if x is a 1, this becomes a 1. A -3 times 1 is -3 plus 3. This is going to be 0. So normally to plot, we only need 2 points. Here we have 3. And I notice this one's off our scale a little bit, so we can just make a few more points there. So if it's a -1, we get a 6. A -1, we get a 6. A 0, we get a 3. So 0, 1, 2, 3. And if it's a 1, we get a 0. So 1 and a 0. Now you'll notice that all of these points are in a straight line. And that is sort of proof of the pudding that these are in fact ordered pairs that are proper for this equation. This is a linear equation. Our values are only to the first power, so we end up with a straight line. This line, and again, there's an infinite number of points in this line. We've only did a graph of 3, but this graph is the physical representation of this algebraic equation. And we got to it by following the protocol of putting a t-chart, putting some points, and then getting values that make the statement true. All right, we'll go on here. And the slide shows a proper graph of it on grid lines. And hopefully you have something like that for your notes. Here is some more background that we've already covered. And they're introducing the standard form that we've mentioned and going through some detail that we've already gone over. When you are graphing, you make a t-chart, get some points, plot them, and in the software in Hawks, the graph will form. And they do test it different ways as you move into practice and certify. So this is example 4, write that. I'll raise it up. And what we're asked to do, and we'll do it together, is graph y equals 2x. Well, again, we want to create a t-chart, and we're going to get some points. Now, often they use a negative value, let's say 1. They always use a 0, and we can use a positive 1 again. So if x is a -1, 2 times -1 is a -2, so y would be a -2. Remember, x is our independent variable we put in, and then once we do that, we get a number on this side, gives us the value for y, which is our dependent variable. Now, if x is 0, y is 0. If x is 1, 2 times 1 is 2, y is 2. So now what we're going to do is graph these, and they have a nice graph here. And lo and behold, they chose sort of what we did. So -1, -2 is over to the left 1, down 2. 0, 0 is our origin, and then 1, 2. So hopefully you've done a little sketch. Yours is going to be somewhat crude because it's a sketch. You want to know the protocol for doing it. Now, as we look at example 5, you're going to write that down. And I'm going to go to a whiteboard here. And a typical equation in standard form, the t-chart I would recommend is something that looks like this. So you have a 0 for the x, then a 0 for the y, and then any other point. This is one that was on the previous slide. We'll go over that shortly. But notice what happens here now. If x here is a 0, 2 times 0 is 0, we get 3y equals 6. Divide both sides by 3, y is going to be 2. Now if y is a 0, 3 times 0 is 0, we get 2x equals 6. Dividing both sides by 2, we get x is going to be a 3. Now if we put a 3 where the x is, this would be 2 times negative 3 plus 3y equals 6. This becomes a negative 6. Transposing that negative 6 to this side becomes a positive 6. I'll write it up here, over here. We get 3y equals 12. This is a negative 6 that we transpose. Positive 6 and 6 gives you a 12. Divide both sides by 3. Y is going to be 4. So we've gotten 3 points. So let's go back to our regular screen, and we're now going to plot these. They have a nice graph here. And I'll take this one off so it's not confusing. So let's see what we have. We have a 0, 2, which is what they chose too, right there. They have a 3, 0, which is right there. And I've used a negative 3 and a 4. There's the negative 3 and a 4. And notice there's an infinite number of points. But when it's in standard form, this is a good protocol to follow. And we want you to sketch this as example 5. Now, we're a little over 20 minutes, but I want you to get this last item as background, and you're going to title it Intercepts. Now, what are intercepts? Well, when we draw a graph, and if it crosses the y-axis at a certain place, that is considered the y-intercept. If it crosses the x-axis at a certain place, that's considered the x-intercept. And often this is an excellent tool for graphing. And they will say, find the intercepts. So you do so by making what is called an x and y intercept t-chart. I want you to name this. What is this called? An x and y intercept t-chart. Put a 0 there by the x, a 0 by the y. That's going to give you the intercepts here. Now, the official way of writing this, and they're kind of hinting it, is 0, comma b. And in the x, y coordinate system, we said the b would be the y, and that's what they're showing. And the proper way to write this one is a, comma 0, where again, the ordered pair AB, the A refers to the x coordinate. Now, what are they? Picking them out from the graph here. Well, when x is 0, we get 1, 2, 3, 4, 5. This is a 5. That is your y-intercept. And here it's 1, 2, 3, 4, 5, also a 5. But on the x-axis, this is your x-intercept. So pause, understand what intercepts are, the use of the t-chart, and that will wrap up this lesson.